Hello, my friends. We are back here speaking with luminaries, influencers in the world of science and consciousness. And my very special guest today is Stephon Alexander. He's a professor of physics at Brown University and the 2020 president of the National Society of Black Physicists. He's also a jazz musician and released his first electronic jazz album, Here Comes Now, with Erin Ryu, and God Particle with bassist Melvin Gibbs. He's the author of The Jazz of Physics, lives in Providence, Rhode Island, and I'm reading his latest book right now, which is Fear of a Black Universe, an outsider's guide to the future of physics. So I have a lot of questions. Actually, I've made some notes here.
Wow, I'm ridiculously flattered. Thank you.
I am privileged to be talking to you. But before we go there, I'd like our audience to know why you wrote this book. What was the intention behind this book, and why this title?
Yeah, wow. It's the first time I've been asked that question, actually. And I wrote the book for a couple of reasons. One was to kind of pay homage to my heroes, to individuals that I felt influenced me and also supported my career. And I felt that I'd come to a place in my career as a scientist where I felt comfortable to expose certain things about my views, my thoughts about not just the science that I had worked on, but also the way that science was done, and also who influenced it and how that science was influenced. And also I felt like it was time for me to, for lack of a better word, come out of the closet. And kind of speak to what got me involved, what got me as a young person into science to begin with, which had to do with really asking the question about what is this reality? Who am I? What is behind science even? How is it that human mind can do what it does to come up with science? And so I think like it was a combination of all those things. And also I felt like I had a little bit of an axe to grind, in the sense of that there was an outsiderness I felt that had to be embraced and celebrated, not only, oh, woe is me type of thing, but more like, oh, it's a celebration. It's actually there are benefits. And I want to explore that. The writing of the book itself, I want to mainly write the book to learn and explore those questions and see that the process of writing may help where it got me in writing of the book. So it was also an experiment for me. That's a long-winded answer, but
no, that's a very wonderful answer. And I've been reading your book very carefully, and I find some amazing insights. And you're kind of unusual in that recently, I've interviewed a lot of physicists on this show, which, by the way, we reach millions of people, and I'm encouraging everyone to get this book and read it if you want to have some insights into the nature of what we think reality is. But, recently, Stephon, I interviewed once again our friend Frank Wilczek, who wrote a new book. That's
one of my heroes, one of my major heroes in physics.
He's great. So one of his new book is called Fundamentals. And in the chapter, in the book, he has another chapter called Fundamentals of Fundamentals, something like that. And then I also interviewed recently from Caltech, what's his name? Carroll's.
Sean. Yep.
Sean.
Another friend.
And they're brilliant people, but they're kind of hesitant to maybe, I'm not sure, hesitant to come out of the closet themselves because we keep asking these questions, these conundrums that seem totally unsolvable. And I'm going to address those in a moment. But you're the first person, actually, whose book I'm reading from a physicist that actually addresses consciousness. None of these other books that I've been reading recently even bothers to address consciousness. And yet, we know that science is an activity in consciousness. Mathematics is an activity in consciousness. And if we're talking about the measurement problem, then, what is it that measures? And I have some issues with even the standard interpretation of measurement that I'll come to in a moment. But for our audience, before we get there, these are some of the chapter headings. And I'm not going to reveal too much about the book because I want people to actually read the book. And but these are very interesting titles. I just want to share with our audience. Part 1, Escape from the Jungle of No Imagination. That's the first chapter. The Changeless Change, Superposition, The Zen of Quantum Fields, Emergence. And then part 2 goes a little bit beyond, beyond this introduction into cosmic improvisations. There was a Big Bang. So what banged? A dark conductor of quantum galaxies, cosmic virtual reality, embracing instabilities, a cosmologist's view of a quantum elephant, where consciousness comes in, the cosmic biosphere, dark ideas of alien life, Into the Cosmic Matrix, and the cosmic mind, and quantum cosmology. These are the titles themselves speak to you. And I encourage my audience to actually read this book if they want to see where consciousness and cosmology come together, which has been a passion of mine forever. And in all, fairness, I'm not a cosmologist, I'm not a physicist, I'm not a mathematician. My training is in medicine, neuroscience, and I've always been interested in the hard problem of consciousness, and it kind of evolved. And so in 2008, I looked up the 125 open questions in science. The first question was, what's the universe made of? And I came to the conclusion that it's a wrong question, that the universe is not made of anything other than it's a human construct for human perceptual activity in human consciousness, because that's how we experience the universe, as sensations, perceptions, images, feelings, and thoughts. The rest is a story. And I had once come across a mathematician from MIT, I forget his name. He was from Europe, and he was very much revered. And we were at a conference at MIT, and somebody said the same thing, what's the universe made of? And he said, there's no such thing. It's a human construct. That's the first time I'd heard that statement, and I pondered over it. And then the second question in open question in science, the first is, what's the universe made of? The second is, what's the biological basis of consciousness? And, my opinion is that's also the wrong question. There's no biological basis of consciousness. Biology is an experience in consciousness. So, I keep collecting these articles that keep appearing in these magazines. This latest issue of Scientific American, and here's one of the articles in this is, the universe is not locally real. And it, I actually talks about the Nobel Prize this year. I'll just read one or two lines. One of the more unsettling discoveries in the past half century is that the universe is not locally real. In this context, real means that objects have definite properties independent of observation. Local means that objects can be influenced only by their surroundings, that any influence cannot travel faster than light. Investigations at the frontier of quantum physics have found that these things cannot both be true. Instead, the evidence shows that objects are not influenced solely by their surroundings, and they may also lack definite properties prior to measurement. So who is it that measures? What is it that measures? What is it that, measures? It's a human observer embodied inside a human body. The more I think about that, the more I realize that there is no one inside the body. I mean, there's no little Deepak looking out of these eyes from somewhere here in the head at the world. And so where is, or what is the observer?
Well, I mean, we have to start with some, some axiom, and then of course, and maybe give them up. But let me begin with an axiom. Let's talk about, say, energy. And let's talk about energy, which is the ability to do something, to do work, right? To act on. But let's talk about energy that is able to localize, right? So in other words, I can imagine energy that is completely delocalized. And we actually know there's a good sense of what that is. Albert Einstein taught us that, causal propagation through space-time is different than space-time itself. That when we look at like the expanding universe, we have this sort of, we have this, I'm going to now impose structures here, but we have this expanding expanse of space-time where we have galactic systems that span hundreds of millions of years that it would take for us to get to those systems. Yet that space exists out there. And it's in that sense, I mean, that space is an example of a delocalized continuum or discretum, if you want to, depend on what side you sit on, all right, that contains energy. That energy actually is revealed by the expansion rate. So the expansion rate, according to Einstein's theory, is the energy actually of that space-time. But that's an example. But when you're saying that make an observation, it seems that for us to be able to do that, we are in an ability to localize, we'll localize form, that energy can actually localize so that in order it can process things out there. So I kind of want to start with that as an axiom to say that I want to agree with you, actually. I'm going to agree with you and say that actually there isn't, this is my own personal view, and I don't think we're there yet in terms of science, but I think quantum mechanics combined with relativity, we already know that if things are made up fundamentally of quantum fields, and quantum fields can organize, and maybe I should back up a little bit and say that the working paradigm that we now know by smashing things together in hadron colliders at the LHC is that fundamentally, when we study the structure and the nature of these things, that everything, all matter that we know of now, are really made up of, they come from fields. And fields can be completely delocalized entities. Their vibrational patterns give rise to what we call matter that's localized. But fields themselves need not be local, right? Fields do carry energy. And I think that thinking about it through that lens is very much, akin to how we think about modern physics, what you're saying there. So I'm going to throw it back to you. How do you now feel about saying, putting your statement, your question, that if we are made up of fields of energy, how do we, the question then becomes, how does that field become localized? And how does it remain localized? So,
the fields that physicists talk about are basically, as you said, quantum fields, They are formless. They have the potential for creation of information, energy, matter, etc. But if you and I, as this body-mind, has to be part of the field, it has to be part of the field. So is it the field that's observing itself? And if it is that, then it's a field of consciousness.
Again, at the end of my book, I came to that conclusion on my own after doing a lot of my own research, of trying to figure out how to reconcile what we know, everything that we know to be true, and from the experiments in modern physics about, starting with the field concept, which is that, and in a nutshell, right? If a field, like for example, the electron field that Paul Dirac discovered, right? So the field responsible whose vibrational pattern gives me an electron, or even the positron as antiparticle, they're both contained in this field. And if you buy this, then every single electron in this universe is coming from the same one field. That's what the equations tell us. There's no, in terms of, I taught quantum field theory at the graduate level this past semester at Brown. That's what the Lagrangian tells us. We have you can predict and compute what this field is doing. And so every single electron, the ones in your body, ones in my body, is all coming from one electron field, right? So that's the first thing. What are the assumptions about this field? Well, there are certain properties that are irreducible, that cannot be reduced to anything. For example, the electric charge, or what we call it's leptonic charge, its mass, we believe, its spin. These properties are irreducible. You cannot reduce it to anything. They're inherent. And so I believe that we have to treat consciousness the same way, that it is part of this field, the electron field, but it's irreducible. Now, beyond that, I don't know how to, I'm at loss with language. Some of the language I picked up for this were actually from some things that actually you in some of your writing and some of the references I looked at, it led me down the portal. I discovered some work by David Chalmers, the idea of panpsychism. And it's kind of really interesting that idea has taken up steam with like some of the leaders in the field, like Christoph Koch, I'm hoping I'm pronouncing his name well, and other leaders, and now in modern neuroscience. So things have really shifted, hasn't it? I mean, what are your thoughts about that? About the idea of endowing now all the fields that we know, the electron field, the gauge fields, the W boson, that the same way that there are things that are irreducible to that charge, spin, these properties you cannot explain it from something else. That why not then endow the notion of the ability for the field to have an internal, for lack of a better word, an internal experience that is consistent with its structure or its complexity, right? So a W boson's consciousness it's not something that I'm not a W boson, I'm made up of many of them. But so anyway, that's kind of the conundrum that I find myself in at the moment.
Let me come to that in the end,
yeah.
okay? Because I have certain conclusions about what you said, but let's come that to the end. I made a list of questions, and these are basically very short answers to these because, or wrong, I don't know. Number one question is there a cause we can ascribe to the Big Bang?
It depends on if the Big Bang is preceded by another event. So for example, if the universe actually underwent a contracting phase into the Bang and then expanded out, there are theories now, there are ideas of what could actually be going on at that moment, called what we call the Big Bounce. One idea I'm very much supportive of and ascribe to is something that was developed by my colleagues, Abai Ashtekar and Martin Boyerwall and collaborators, where you can actually have a quantum bounce. Like quantum physics turns on and makes gravity, makes space-time fuzzy, and that leads to this ability to avoid the Big Bang singularity and come out into a bounce.
So then that would lead to the second question. If it is a big bounce, then why did it happen when it happened? 13.8 billion years. Why not 20 billion years ago or earlier than that? Does that question even make sense?
It does. And it actually is a fantastic question, because that question will actually help us understand certain relationships. So, for example, one of the things we look for in physics is how one force might be related to another force. So that eon, that period of time actually we can get that actually from the expansion rate of the universe and the duration of that expansion and the strength of the gravitational coupling. So by knowing that, actually, we'll be able to relate that to the other question, which is, what does gravity have to do with the other interaction? And what was the role of those other forces as gravity, like those other forces become unified with gravity? So that's actually a very good question for the physics, actually. We would like to know that to help us relate to the other forces.
Okay, I get that. Now, when I ask physicists, where did it happen? They say it happened everywhere all at the same time. They talk about the cosmic background radiation coming to us from all sides. So it happened all at once and everywhere, which kind of is mind-boggling. And and then what did time begin with that? And so did the Big Bang contain all of space-time at the moment it occurred?
So to go back to and push back at some of my colleagues that said that the Big Bang happened everywhere, that presumes that the notion of where even existed at the Big Bang. So it could have happened that the Big Bang happened nowhere, depending on what framework we're working on. There are now theories that we work on that requires a way of talking about the Big Bang with no space-time, actually. These are called so-called matrix quantum mechanics. The second thing I want to say, that doesn't get our audience members here any closer to the truth, closer to understanding, but I'm just putting it out there that there are other concepts out there. The second thing is, yes, the idea of time, we call this a problem of time, and how to reconcile time with the expanding universe is very much a model-dependent construct and statement. So there's a sense in which general relativity is a timeless system. Okay, I mean the description of Einstein's description of a curved space-time. It turns out that time is actually some type of fake, some type of redundant variable, and we then have to figure out how to reintroduce, time into that. And there are various physicists that have ideas. I have my own idea. Wrote a paper about this last year, but one idea is that you can use the matter fields in some ways as a relational clock, that the fact that this thing in relation to the space-time gives one the impression that time is actually advancing, but in totality, nothing's actually happening.
Is this problem that we call the cosmological constant and the measured value and the theoretical value are off by, 1 to the power of whatever, 120. Is that an issue in our calculations of what we call reality? I mean, isn't the cosmological constant the same thing as what you call dark energy these days, right?
That's right. They're synonymous with each other.
And that's
just that one sounds cooler than the other.
Okay. Now, is that supposed to be 70% of the universe, right?
Correct, yes.
And so what is it? Is it something that we can actually put a handle on? I mean, what is this thing that is expanding? And we are told it's the space between galaxies that's expanding. And even as it's expanding, space-time is being created. But then there's this problem that, the measured value and the theoretical value are totally off. They don't agree with each other.
Yeah, well, one of the greatest theoretical physicists on the planet, I mean, some consider him to be the greatest, said that the cosmological constant problem is one of the biggest embarrassments of physics. That's Edward Witten, one of my heroes. And I agree with him, you know, and I think that the embarrassment is the following, as far as I'm concerned, is that the calculations that we use to evaluate the value, the inferred value of the cosmological constant, right, are the same precision calculations. And let me give an example. You as a medical doctor, you use tools of precision to maybe do an operation or to, you know, to diagnose, and you know that that tool has a certain precision, right? Like, you know, every time I do this, this happens. Imagine that I say in physics, we have similar tools of precision. And those tools tell us, for example, exactly what should happen if an electron and a positron run into each other and annihilate. I'm going to produce a slew of these particles in these circumstances at this energy. And how precise? I'm talking about 12 decimal points of accuracy, that the theory will produce 0, 0, 1, 1, 2, 3, whatever, all the way up to 12 decimal points. And I can measure based on that theory, all right, quantum field theory, I can measure that with the theoretical prediction of that calculation with that experimental precision, right? Those same calculations that we use to evaluate the cosmological constant problem, right, turn out to be embarrassingly 120 decimal points off. All right, so that's the nature of the embarrassment, that the very physics that we trust so much with the precision turns out to fail when it comes to talking about the quantum mechanical contributions to gravity. So what we believe is going on in this embarrassment is that we don't really understand gravity and how gravity and quantum mechanics talk. It goes further than that. And the second thing I'll add to that is, what is the dark energy or the cosmological constant? That's an interesting question. Many physicists so far believe it's some unknown field. And whatever this field is that's imparting the kind of energy to accelerate space-time, it has the magical powers to really fix these embarrassments that we have. And we're just not smart enough to understand its nature. And I think part of the truth is that I do believe the cosmological constant is some kind of field, but whatever kind of field it is, it's much more clever than our ability to discern its properties.
So, you know, talking about precision, this thing that you call cosmic inflation, that presumably, you know, my notes say happened from 10 to the power of minus 37 to minus 34 times 0, when the universe tripled every trillionth of a trillionth of a trillionth of a second, and then slowed down suddenly. And this is so precise that is there any explanation for this precision?
No, not at the moment. I mean, in cosmic inflation, as you know, invented by one of my mentors, Alan Guth at MIT, was designed actually not to say a thing about cosmology, but to solve this other problem in grand unified theories. You heard about, remember these ideas of guts, right? Grand unified theories. But it led to a prediction. And the prediction it led to was that the quantum fluctuations that are produced during this epoch of rapid, as you said, this rapid expansion and doubling of space-time, in the wink of an eye, like, you know, the universe just gets macroscopic from being this very tiny subatomic state, that the predictions was explain actually the origins of that these quantum undulations grew as sound waves in the background radiation into the stars and galaxies. And that prediction really does, agrees with the observations that we've made. So we know there's something like inflation going on. However, we don't know the correct theory of inflation. And in fact, one of the things that's going on as we speak is this attempt to unify or to bring together two mysteries. The mystery of the Higgs particle, which I'm sure you, I wouldn't be surprised if it's one more of your queries in this conversation. But this Higgs particle, maybe the Higgs particle and the inflaton are really one and the same thing. And if that's the case, it could be that actually, Deepak, it could be that inflation might actually not be taking place at the Planck era, but which is, you know, T, as he said, 10 to the minus 30 something seconds in that range, but actually in the electroweak era, right? So now we're not talking about the, you know, what we thought inflation to be taking place in terms of energy scales, you know, 10 to the 16, right? Which is like, you add what, 3 or 4 zeros to a trillion electron volts, right? Sometimes we call that, you know, giga electron volts, which means a billion electron volts. So you have 10 and 16 exponents, billion electron volts. We now, there are theories on the market, I'm working on one of them as well, where we might think that inflation actually happened or more at the scales that we're getting closer to, that the Large Hadron Collider is accessing. This is the, did I say giga electron volts? I meant to say 10, now in the order of a billion electron volts, 10, you know, like 100 TeV. Because the inflaton might actually be the Higgs particle. But anyway, those are just theoretical ideas.
There's this whole epoch that we call the Planck epoch, 10 to the power of minus 43 seconds.
Yes, yes.
When there are no laws of physics, and then suddenly they appear.
Yeah, that's a mystery.
Cosmic.
John Wheeler had an idea that actually, of like basically that the laws of physics themselves, that a singularity is actually where the laws are just, they become lawless. Like there's just no laws. The singularity defines actually that.
What about mathematics? Where does mathematics exist? Why is it so unreasonably accurate in describing the cosmos? As was it Eugene Wigner who wrote that article? Somebody wrote the article, The Unreasonable Effectiveness of Mathematics. Is mathematics not an activity in consciousness?
Yeah, I mean, you know, one of my heroes in mathematics, and his mathematics plays a big role in string theory and foundational in string theory. You know, when I started to delve into him and is Ramanujan. Yeah. And like, I mean, I don't know. I mean, any accounts I read was that he'd actually, the kind of math, which is like next level math that even I have friends who are like, you know, I have a friend that is a Fields medalist, and he follows Ramanujan's work. He's like, I have no idea where that comes from, but I did read that he dreamt, like dreams would play a role in his math, in actually his mathematical discoveries itself, which is just completely makes me realize, and that combined with, yeah, that there, for some physics, not all physics, but the type of physics that I do, it is uncanny. I mean, for example, you know, in group theory, which is a mathematics, that's a mathematics of symmetry properties, right? Group theory, like, you know, the group, the rotation group, for example, describes the symmetry principle of isotropic rotations in 3 dimensions. There are all these groups. Group theory, the mathematics of symmetry, has a concept called the representation. So, you know, if I have this abstract group that tells me how to rotate objects, the objects that are being rotated have a mathematical name called, these are representations of the types of objects. So I can rotate a vector, yada, yada, yada. Now, there's a concept of what we call an irreducible representation in group theory. And it just so happens that those representations, coincidentally, I provide to you a mathematical group. So the group, for example, rotational, SU2, the Lorentz group of space-time. It's nuts that Paul Dirac discovered that the irreducible representation is the spin of the electron, is literally, or the quarks. The 3 quarks come from the group SU3, Merrill-Germain. These are the fundamental representation ought to be interpreted as the quarks themselves. And to me, there is this really weird thing about what Vigna said. And I could never, like, you know, have the quote exactly. However, I think that combined with Ramanujan, like these great mathematicians, Grothendieck is another example, where that's right. I mean, the math that they were doing were happening at some other level of consciousness or within some other situation. In my case, I've definitely had very rare instances where a combination of me doing calculations and maybe I had a dream, and in this dream, some kind of object or some intuition came. I may have remembered it, and it did play a role in the solutions I may have found. And this is not uncommon. My colleague, Jim Gates, one of my mentors, he feels the same way. So I do agree, but it's so mysterious. It begs a bigger question, right? It's sort of like, it makes me feel even more like that there's even a deeper mystery about the activity and the discoveries we make in physics and mathematics and science, and our role as human beings in actually being able to access those things, those truths.
You know, I was thinking, you just mentioned Ramanujan, but isn't Ramanujan an example of, say, Gödel's theorem in a way? That there are these theorems that are true but can't be proved. They just kind of pop up in the mathematician's awareness. They sound intuitively true. And if they're accepted, then you can proceed with the algorithm. If they're not, then you're stymied. But the theorem suddenly pops up. It's not a logical extension of the previous theorem, and yet it's true, it works. So that, to me, anyway, suggests creativity in the cosmos, you know, because here you are, you suddenly have a disruption, a discontinuity in logic, and you come up with this mathematical formulation that is true, but it doesn't logically come from the previous formulation. Does that suggest creativity in the cosmos?
Absolutely, it does.
Okay.
Because, I mean, we are, you know, like if you buy modern cosmology, there was a moment, like, you know, going back to the CMB, you know, roughly 13.8 billion years ago, where there were no humans, there were no planets. And we can look at this data and see a field of, like, you know, baryonic oscillation, plasma oscillation, energetic at that temperature. And as the universe cooled, it did form stars and galaxies and people. So we are, I mean, we and the stars and the galaxies, right? We are an activity of the universe. We're not separate in that sense. The universe created, you know, that was an act of creation of the universe, creating, you know, creating the complex of galaxies and stars and planets and us. And it's, for me, I know it's, I sort of, there's a sense in which there are times I'm like, yeah, I'm this individual doing my thing. But there are times I'm like, wait a minute, who's doing who here? I mean, you know, we're flinging around in outer space. Dark matter's doing its job. I mean, the universe is doing this job, right? And it's also doing me, you know, and I can't run away from that fact.
So as I was, you know,
that the universe is creative by definition. If we're creative, the universe is creative. Yeah.
Yeah. So, you know, when I talk to, say, Sean Carroll, his latest book, Something Deeply Hidden, and now he's got a new book, but he proposed, when I spoke to him, infinite universes. Then you look at some of the writings that are coming out right now, they say there are 2 trillion galaxies, 700 sextillion stars, uncountable trillions of planets, probably 60 billion habitable planets just in the Milky Way galaxy. Now, you know, and then you go on Wikipedia and you look at the theories or interpretations of quantum mechanics, you have 30 or so. You know, I was brought up reading books like this, Too Big for a Single Mind, the ideas of the pioneers of quantum physics, all the original ideas.
Well, I got to get that book. I'm looking
It's
for that
actually
type
a
of book.
history of all the pioneers.
No,
It's
I got
very
that.
interesting, too big for a single mind. But these pioneers, in a way, with all subscribe to the Copenhagen interpretation, which needs consciousness to cause measurement and collapse of the wave function. But then you have string theorists who talk about eternal inflation and infinite universes. And now you have these telescopes out there looking for biospheres and Goldilocks zone, who propose that there might be 60 billion habitable planets just in the Milky Way galaxy. You multiply that by 2 trillion galaxies, and it's mind-boggling. Who are we on this planet? If we were looking at all the beaches of the world, and our planet would not even be a speck of dust or 1 grain of sand in all the beaches. And on this speck of dust, a grain of sand, there's a species called Homo sapiens who's trying to figure this all out. And Homo sapiens has only been around, say, 200,000 years and has had a cortical brain for maybe 4 million years. We trust this brain to give us an experience of what we call reality, but the brain itself has its own limitations. You know, we have a narrow bandwidth of perceptual activity that we interpret as reality. And there are other species. You know, what does the world look like to a snake or to a bat or to an octopus? You know, what is that experience? Is there actually a physical world, or is this all a human construct for modes of knowing and experience in a limited human consciousness? Because before you can call something whatever, gravity, electrons, protons, Higgs fields, you have to have some experience or some knowing in awareness. And then once you have that experience of knowing in awareness, you can give it a name. You can give it call it an electron. But that's a construct for a mode of knowing and experience in our awareness. So are we actually ever getting closer to what we call fundamental truth? You know, when I asked Wilczek in his chapter on fundamentals of fundamentals, he says that there are 3 fundamentals that create the whole universe. And he calls them spin, charge, and mass.
Right. Yep.
Spin, charge, and inertia. But then he goes on to say these are dimensionless entities that have no location in space and time. So, you know, when I read eternal inflation, when I read string theory, when I read dark energy, dark matter, are these even knowables, or these are just postulates or constructs in our awareness to make some sense of this mystery that we call existence? Because there's existence, but there's also awareness of existence. If there was no awareness of existence, then for all practical purposes, there is no knowledge of existence.
Well, I agree. So I think that one of the useful things about the scientific enterprise and actually doing the experiments and coming and having theories that can, say, explain a wide range of phenomena that we do both experience and actually test experimentally, right, is that what it does do, for me, it does 2 things. First of all, we come to now learn that there are concepts like quantum mechanics that the fact that we discovered it, you know, we human beings discovered this thing, that it even transcends our mind's ability to conceive of it, to actually understand it fully, to actually, and the things it's saying about what, you know, how we should perceive reality. Well, at least this person, I have not perceived reality that way. So I think one thing that's very interesting is that dance between sort of, as you said, so I agree with I think with what I'm hearing, which is that we can only know this world. Stephon Alexander, you know, can only know this world. At the end of the day, even if I do an experiment, it has to be registered through my consciousness, through my perception, right? That I have to have a qualia of those things. And that, but at the same time, I do have, there is something about this mysterious mind. As a fellow human being, we claim we can share this knowledge, we can come to discover these laws that are exactly saying that there are phenomena that's outside our ability to perceive. And to me, as Albert Einstein said, is one of the biggest mysteries, is that we can, this limited apparatus can come to know some of that stuff that points exactly to the paradox that we cannot perceive those very things that those theories are predicting. What are your thoughts about that?
Well, I can tell you that the more I learn, the more bewildered I am. The more bewildered I am. There was a
and that's saying a lot. I was saying a lot because I've read, one of my favorite books of yours. I'll never forget. I said drive from Penn State when I was a professor there to New York City, just to get some life. Even though I did like that area, and at that point I was going through a lot of some difficult times in my life. And you had a book, it was an audiobook that I bought because I keep myself company with audio. You had a book about Siddhartha.
Yes.
I had a book, and I've read other books about, including the Herman. It was, I think, one of the best takes. You had such a deep understanding of the, through writing that book about him and about, it really took me there. And I just remember crying, and that's an example of there was some universal truth about his life. And as you were saying this, I was also thinking about this ability, though, for us, some human beings who have an ability to actually know something or perceive beyond. I wanted to bring the conversation also to that point, because that book did have a big influence on me.
Well,
and the story of the Buddha.
Yeah, the story of the Buddha is extraordinary because, he was the first person to suggest, at least in Eastern wisdom traditions, that what we call everyday reality is a lucid dream in a vivid now. Okay, so if I asked you...
Did he actually say something like that?
His last words were, "This lifetime of ours is transient as autumn clouds. To watch the birth and death of beings is like looking at the movements of a dance. A lifetime is like a flash of lightning in the sky, rushing by like a torrent down the steep mountain." Now, Wittgenstein said something similar. He said, our life is a dream. We are asleep, but once in a while we wake up enough to know that we're dreaming. And that leads me to the final conundrum here. A few years ago, I wrote to Freeman Dyson. This was before he passed on, because as you know, he was one of the most brilliant scientists ever.
Yes, he was. Yes.
I asked him to explain a quote.
Schwinger-Dyson equations. Wow, what a beautiful thing it is.
Yeah, so I was reading his book where he said every quantum experiment forces the atom to make a choice. So I asked him to explain that to me. Every quantum experiment forces the atom to make a choice or the particle to make a choice. So I wrote to him. He was very kind to answer. He said, there are 3 riddles that have occupied me all my life. Number 1, the unpredictable movement of particles. He didn't say random. He said unpredictable. Now, there's a very fine thing over there. Random inherently means inherently random. Unpredictable means it appears random to me, but I don't know what's going on. So he said the unpredictable movement of particles, number 1. Number 2, a universe fine-tuned for mind and life. And number 3, our own consciousness. He said, I don't know what the solution to these riddles is, but I think they're connected to each other. And he left it to that. and I preserved that email for posterity because that's where we are right now. It's a riddle, it's a mystery, and maybe the closer we get to truth, we're actually expanding the mystery of creation. And so I want to conclude this by asking you, of the 30 or so interpretations of quantum mechanics, which one do you favor? Eternal inflation, string theory, decoherence, Copenhagen? Which one do you favor and why?
I've gone back and forth, and let me first say that I claim complete idiocy and ignorance about, my understanding of quantum mechanics. And that's really sad.
I'm talking to an expert.
I've taught the class for many years, and my students probably will see this and laugh at me because they just took a final exam not too long ago. Who is this guy to give me this exam? But I would say that, when I think about all the approaches, I think, I was not a fan of the Copenhagen, of Bohr's interpretation, but I think it's pointing to something like that. I think it's pointing to something like that. And I think that this idea that Wigner and von Neumann were on to something as well, that we have to reconcile the role of scientifically, if we can ever get it, the role of actually conscious energy, or that interacting with quantum systems, or not, maybe the word interacting is not the appropriate, the correct word, but that relationship in terms of how an experimental apparatus, or what we assume to be a classical observer making measurements on quantum system, as you said, who is doing the measurement, right? Is, I think, gonna be one of the big questions moving forward, and its role to what we call non-locality in space-time and gravity, how that is also related to the fundamental question of how do we reconcile quantum mechanics with space-time, or the program of quantum gravity. I think we're in for some really interesting, a big ride, an interesting journey. But I do think, and as a physicist and as a scientist, that our process of exploring and investigating as scientists and the tools that we have, but keeping an open mind and being humble, that we will expand on that question and have some deeper understanding. But I agree with you that it may actually open up even more wormholes, for lack of a better word.
So, Stephen, it's been a pleasure speaking to you. We have to conclude because we can't go for more than an hour in the format we have.
But this was fun.
I think maybe we need to relook at some of the ways we make assumptions in science. So right now, I think all of science is based on what has been called in the philosophy of science naive realism. And that is based on several things. The picture of the world is exactly what it looks like to human beings, number one. Number two, the universe is made out of matter. Nobody's experienced a substance called matter. We only experience our perceptions. And number three, subject-object split. There's me and the universe when the subject itself is an expression of the universe. So expanding the tenet, the area of science to not just what is being observed, but who or what is observing would maybe expand our ability to unravel at least some of these mysteries.
I am sympathetic, and I agree with that sentiment. And I agree about keeping an open mind and really staring hard at the assumptions that we made, especially those.
My very special guest has been Stephon Alexander, professor of physics at Brown University, very accomplished physicist, mathematician, theoretical physicist, jazz musician, explorer of consciousness. There's a lot of amazing stuff in this book. Please pick it up and read it. And I promise you, you won't be disappointed. You might be bewildered even more, but that's a good thing. I think, I end with a quote from my favorite poet, Rumi, says, exchange your cleverness for bewilderment. And if we start with bewilderment, we have some hope. And that's the scientific quest as well. Thank you, Stephen, for joining me. It's been a great pleasure and a privilege to speak to you.
Thank you, Deepak.